Yes, 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 very well.
Okay, so good afternoon again. So today I want to continue these two lectures with something quite different from yesterday, where the focus was on working through some of the fundamental concepts, a bit of mathematics. Today there won't be much mathematics, but I want to talk much more about nuclear beams in the LHC, also a little bit at RIC, and to give you a feeling and some understanding of the things which will be important in the LHC heavy ion program from the point of view of experimenters. So just a few words to set the scene about nuclear beams, the energy and the luminosity. We always, in our calculations, have to look at the mass of the ions or nuclei, fully stripped ions that we have in the LHC. They have a charge Q times the basic electronic charge and mass M, and a nucleon number or mass, so-called mass number A. We mainly collide fully stripped ions such as lead 208 with Z equals 82 and A equals 208. The mass of one of these nuclei is given by the usual mass that you get from the tables for this isotope, minus the mass of the electrons, which is 193.7 GeV over c squared. People very often use 208 times the proton mass as an approximation. It's not a very good one and can get you into trouble in accelerator physics, where some calculations at least have to be done quite precisely. The binding energy of the 82 electrons is less than 1 MeV, so this approximation is actually good enough. So when we talk about the ions, the energy of the ions or nuclei and nucleons, we have to be a little bit careful. This is a common source of confusion. Of course, you basically just have a particle with a charge ZE and a mass M. Its total momentum squared is given by the usual relativistic formulas. However, you have to watch out that especially in low energy ion accelerators, when people quote the energy, they sometimes don't specify what they're quoting, but what they usually quote is the kinetic energy per nucleon. So this is the total energy divided by A, the total energy minus the rest energy divided by A, which is approximately E over A at very high energies. But if you look at the low energy injectors, this will be quite different. So at the LHC, we avoid confusion by never using any kind of energy per nucleon in calculations and just quote it at the end. And we use these notations. E is very closely equal to momentum times C, which at the nominal maximum energy is 7 times Z TeV. So we write it like this. It's actually 574 TeV. Or when we quote numbers for the physics community, for example, we are usually asked for energy per nucleon, and we tend to write it as 2.76 ATV. Then, of course, there are the collision energies. If you imagine colliding two different species, A1Z1 and A2Z2, the total center of mass energy is given by this, and since the momenta of the two beams are not equal, you have a velocity of the center of mass of the total colliding system. This will be very large. It's actually in the case of lead, and smaller for protons. This is the rapidity of the center of mass of the system. Actually, it's nice to note that when we reached 6.5 TeV per beam, ZTeV per beam in 2015, the LHC actually attained a total collision energy of just over 1 PeV, so a very large quantity of energy in cubic centimeter scale volumes. Of course, if you look at colliding nucleon pairs, which is usually done by the experiments, you have to divide everything through by the A's, and the center of mass energy is lower. It's about 5 TeV per colliding nucleon pair, and the velocity of the center of mass, or the rapidity of those colliding nucleon pairs, is given by this formula, which I think you can easily derive. There was a course on relativistic kinematics. I'm not sure if it covered this, but it's a good exercise otherwise. So yes. So for the LHC, the program so far has operated at several different energies. In the beginning, the total energy was low. The magnetic fields in the machine corresponded to 3.5 TeV or 4 TeV protons in the early years. The very first proton lead run was done with 4 ZTeV. And that gave a center of mass energy in proton lead collisions of 5.02 TeV back in 2013. And this energy has come back again because in 2015 and 2018, we adjusted the magnetic fields slightly below the maximum value, which was then 6.5 to 6.37, so as to reproduce that center of mass energy per colliding nucleon-pair, although maximum energy runs were also done, which of course allows people in the experiments to compare proton-lead collisions and lead-lead collisions at the same center of mass energy per colliding nucleon-pair. And of course, there are also proton-proton runs at the same energy, which is less than the maximum PP energy, of course. In future, in run 3, we're going to be running with the maximum potential energy of 6.8 ZTV. So that will give 5.36. There's still a little discussion about whether perhaps to stay at this energy again, not only for comparison, but also for some performance limits reasons. And in future, there will also be oxygen-oxygen collisions in 2023 during run 3, and that will produce these energies also for proton-oxygen collisions. So there are relations among all the runs. It's not just a matter of colliding at maximum energy. Luminosity, of course, you've heard about. This is perhaps the simplest version for the formula for luminosity, with colliding head-on beams. The luminosity is given by the number of particles per bunch times the number of bunch collisions that occur per revolution period of the machine, the revolution frequency of the beams, the gamma, and well, the gamma comes in here because what matters here is the effective cross-section of the beams, which is 4 pi times the RMS sizes in X and Y in the simplest case. This is related to the so-called normalized emittance epsilon sub n through these formulas here. Epsilon sub n is normally quoted rather than the geometric. I think somebody needs to mute, I think, somewhere. Please. Then the geometric emittance I introduced yesterday, it scales with the gammas. And in fact, to 0th order, this quantity is constant as you ramp beams with energy in a hadron machine. That's why we often quote it. So you can rewrite the luminosity like this. If the beams are colliding at an angle, as indeed they are in the LHC, there is another factor which can be derived by doing some integrals involving the crossing angle and the longitudinal length, the bunch length, and the beam size at the collision points. So obviously, to maximize luminosity, we need large bunch populations, many bunches colliding, and a small beam size at the collision point, hence the small beta star that I showed yesterday. Usually beta is equal in X and Y at the collision point in a hadron machine. And then the collision rate for hadronic collisions is the luminosity times the relevant cross-section, which is about 7.8 barns for lead-lead at the LHC. And of course, the goal is to maximize time-integrated luminosity over the running time available. Just for reference, these are the original LHC design parameters, which give the scale of luminosity at the LHC. The design luminosity was 1 × 10⁻²7, which is also the maximum saturation luminosity of the Alice TPC in its first incarnation in runs 1 and 2. The energy per nucleon was this, corresponding to 7 ZTV. The number of lead ions per bunch was believed was 7 × 10⁻⁷ nominally. beta star was down to 0.5 or 0.55 meters at the collision points. The normalized emittance was 1.5 micrometers. I haven't discussed longitudinal emittance, and the rate of removal of particles from the beam is equal to the luminosity times the total cross section, which is much larger than that hadronic one. I'll come back to this, actually 520 barns. So the beam lifetimes are just a few hours, depending how, depending on the luminosity and the bunch intensities. So in high luminosity lead operation, the lifetimes of the beams are quite short, and fills are just a few hours. Luminosity with nuclei and nucleons. The luminosities we quote seem small compared to the PP or electron positron. The PP nominal luminosity was 10 to the 34 compared to this 10 to the 27 for lead. But comparisons are actually more meaningful on the basis of nucleon-pair luminosities. And those are, well, this is actually a luminosity achieved later in lead 5 times the original design. If you multiply by A1 and A2 of the colliding beams, you get the luminosity in terms of nucleons. You have to be a bit careful looking at quoted numbers. This is a useful quantity to compare luminosities for different colliding species. The lead luminosity then becomes closer to the proton one, but if you want to compare, say, oxygen collisions, you have to look at this. And you should be aware, if you look at that the electron-ion collider, people nearly always quote the nucleon luminosity. Here, for example, is a plot showing the history of RIC luminosity with lots of different colliding species they've had over the years. And they show the average luminosity in one store, one fill, the average integrated luminosity in nucleon units. So in ordinary luminosity of nucleus, these numbers would be less, but by different factors depending on the species. So now I want to turn to the story of lead-lead collisions at LHC. And this is still a future collider because there's a lot still to come. To provide the beams to the LHC, we have the LHC ion injector chain, which is partly common with protons, but partly especially specialized for heavy ions. It starts with an electron cyclotron resonance ion source, which was commissioned in 2005. This provides lead 29 plus ions to the RF quadrupole and LINAC 3, which adapts it to the injection of energy of the next machine. This is LINAC 3, the source here, which the beam is then injected into LEIR. Like here, LEIR, it's in a strange position with respect to LINAC 3, but this is for historical reasons because previously it was an anti-proton ring and was substantially modified into the ion ring. This is a very special machine which accumulates and cools the LINAC 3 beam and prepares the bunch structure for the CERN PS. Now, from here on in the PS, the injector machines are the same ones that are used for protons. This is the old CERN PS commissioned back in 1959. Of course, upgraded a lot since then. This defines the bunch structure for the LHC, and afterwards one strips to lead 82 plus in the transfer line to the SPS, which then defines the complete filling scheme of the LHC. This was the Ions for LHC project ran up till 2010 to construct these injectors and adapt them. They play a vital role in creating the high brightness. Brightness is defined as the beam population divided by the emittance needed by the LHC, which is much more demanding type of beam to create than you need for fixed target experiments where the emittance doesn't matter very much. It already delivered the so-called early beam with parameters significantly beyond its design back in the first lead run in 2010. And it was later commissioned for the more complex nominal beam with trains of bunches injected into the LHC. And there have been many performance improvements in runs 1 and 2. Recently in Long Shutdown 2, there were substantial upgrades of the injector, something completely new in CERN. The slip stacking of the bunches in the SPS will provide more bunches and more intense beams needed for the so-called high luminosity LHC level of performance. HLLHC is supposedly starting after in run 4 in 2026 or so. But in fact, all the upgrades for lead-lead are already completed, and one can expect the new level of performance already next year when we restart. So there have been some very interesting developments. The slip stacking was just implemented successfully last week, just a few days ago. And I would recommend that if you can attend the forthcoming Alice Week, you should hear a talk about that on the 29th of November, very soon. So I recommend that to you. This is just a picture of LEIR showing what a complex, but small but complex machine it is. It has a complicated injection scheme of injecting extremely long bunches, which are longer than the circumference, but then compressed longitudinally. There's electron cooling, a special vacuum system, many things. It could be a whole talk on its own. This, just for reference, is the original specification of the injector chain. You see that I just want to convey an impression of how difficult it is to predict the intensity that you're finally going to get after all these stages. There are inefficiencies of transfer from one machine to the other, many different intensity limits that come in at different stages. It's a long story, but here is an indication of how the beams are produced for the LHC. They're built up from batches that are constructed in the PS. These batches, this is for the scheme that was used in 2015. The bunches are separated in time by 100 nanoseconds. Batches are separated by 150 nanoseconds. And those are then accumulated. The PS batches are accumulated in the SPS to make trains. Those long trains are injected several times into the LHC until they fill the circumference. So there are many parameters one can play with here. The longer beams spend at injection energy in the SPS, for example, the more they degrade. So you may not want to inject many batches of the PS into one SPS train. You have to optimize this. And then there's also a degradation in the LHC at injection from various effects. So you have to think about how you're going to do the construction. This is a fairly complex question. I just want to give an indication of how it goes. In the 2018 run, we made a transition from the 100 nanosecond separation to 75 nanosecond separation, which gave almost the peak luminosity that we need for the future run 3 and run 4, although it's not the scheme we will use. This shows the filling scheme of the batches of the SPS seen in the LHC. This is what a train looks like zoomed in, one SPS train. This is for the future with the slip stacking, which inserts 2 trains, one on top of the other. Again, see the talk in Alice Week. This is the complete structure in the LHC, and this is what you see in the 4 experiments. The red one is Alice. This is essentially 1 revolution time. You see all the trains going by. Where they are not grayed out, there is collisions happen. So you see that in Alice, with this particular scheme, you would see a lot of collisions, but there would be some trains missing each other. This is because of the numerology of the positions of the interaction points. Those ones were moved so that you get some collisions in LHCb, otherwise there would be none at all in LHCb. So designing these schemes is a question of sharing out the collisions among the different experiments. LHCb gets the fewest. It was the latest experiment to come to the heavy ion party. So, and it has less luminosity requirements anyway. So different numbers of bunches actually collide in the experiments. Commissioning the beams in the LHC goes actually remarkably fast. People, before the LHC was built, people were skeptical as to whether one could commission the heavy ion operating schemes within the 1 month runs that we have for operation. In fact, the very first run was, we started on a Thursday evening and provided physics conditions by Monday morning. It was done in a few days by very, very careful strategies. There's a lot of setup. A lot of what's done in the setup is checking out the collimation system so that one can control the losses, beam losses, safely. It's a subject I don't have time to cover today, but it's very important. One has to commission also all the optics for the injection, the ramp of the energies, and the squeeze to the collision optics that I talked about yesterday. At the beginning, we kept the optics very close to the proton ones to speed things through, but now they are completely different, and with more efficiency and experience, the commissioning still goes very fast. In future, there will be a separate optics cycle maintained for heavy ions and protons. These were the very first stable beams for lead-lead in 2010. So what's different between protons and heavy ion beams? The optics is in principle similar, but the details are different. The charge per bunch is usually only 10% of what we have in the proton bunches or so. So the impedance-driven collective effects that one worries about for protons are not so much of a problem. Traditional beam-beam effects from the beams interacting are also relatively weak. Space charge, the self fields of the beams interacting with themselves, are important to the lower energy machines, but not the LHC. However, the difference is that we have a large charge per particle, 82 times more than for protons, and most of the interesting beam physics is due to this, in particular intra-beam scattering, which is multiple small angle Coulomb scattering within the bunches, and new beam-beam effects from ultra-peripheral nuclear collisions I'll discuss later. Intra-beam scattering, the theory due to Bjorken and Mutingwa and others can be summarized like this. The emittances grow according to a formula which the main beam parameters come into these factors. These are complicated integrals over the optics of the machine, which I'm not showing. But you can see that high charge particles are much more subject to this. So the growth times of the emittances are between half an hour to a few hours, depending on the parameters in the LHC at injection and also in collisions. We model these emittance evolutions together with the evolution of the other parameters that come into luminosity. One interesting thing about the LHC is that the energies are high enough that synchrotron radiation becomes important for hadrons and even for lead nuclei, which is sort of counterintuitive because it's supposed to only be important for light particles, but here again, the charge plays a role. The total loss per ion is 162 times more than for a proton. And the radiation damping, which is an effect that causes the emittances to shrink and therefore counteracts the intra-beam scattering, is twice as fast, and again has a time scale of a few hours. So this can even be fast enough to overcome IBS at full energy and intensity. This was quite exciting. In the very first ramp of the beams in the LHC, we were the first people to see synchrotron radiation from nuclear beams. It's only previously been seen from electrons, protons, and their antiparticles. This is an image from the very beginning of the LHC operation showing this light appearing as the beams went through an energy of about a TeV or so. Here is one example of a high luminosity fill from 2018 with the 100 nanosecond filling scheme. You see here the luminosity decaying very rapidly over a few hours in Atlas and CMS, these high values. At Alice, the luminosity stayed approximately constant because we separate the beams to level the luminosity, because Alice, before the upgrade, could only accept 1 × 10⁻²7. So Alice in the past got less luminosity than Atlas and CMS because of this. Okay, so, but in the future, this is going to change. There's a paper here which describes the luminosity models and gives references to the details. This was just published earlier this year, comparing the models with the experience in the LHC, and they're rather good. These are some simulation results showing, not with somewhat different parameters. This is for future operation. This is the intensity. This is the what goes on inside. These are the emittances increasing due to IBS and then decreasing again a little bit because of radiation damping in the horizontal plane. In the vertical plane, only radiation damping is really important. So the emittance shrinks. We've actually seen this in the LHC. And this is the number of particles per bunch decaying rapidly because of luminosity. Again, there are many scenarios depending how you do the luminosity sharing and so on. I won't go into detail. This is a global picture of the last lead-lead run in 2018. You can see what happened. This is a period of 1 month, approximately. Unlike proton-proton operation or the sort of operation one had at the Tevatron, it's not months and months of continuous accumulation of luminosity with small tweaks of the parameters by the operators to improve, but essentially constant conditions. You can see that during these 1 month runs, we change things a great deal all the time. And there's a lot going on. We increased the number of bunches. There were problems at the beginning with the source. We had a ramp up then at the time when we reversed the direction of the ALICE spectrometer, and we have to somewhat recommission for a slightly different configuration. There's a pause in the middle. We also refilled the ion source with the lead pellets. And then there was considerable increase in luminosity. You can see the ALICE luminosity, the purple lines here, because it was leveled, but the leveling times became longer, and the peak luminosities in ATLAS and CMS became higher. This was the best run so far, and we got up to 6.4 times 10 to the 27, so 6 times the design luminosity, which is, I think, remarkable, given that the total running time was only 5 months or so in the 10 years of run 1 and 2. This is the LHC status screen, LHC page 1, showing the peak luminosity fills that happened. You'll often see these screens during operation. This is the intensity decaying, which we can simulate quite well, and this is the luminosity decaying. In LHCb here in ALICE, we keep it constant until eventually we do have to allow it to decay. But in future, ALICE will be up here with ATLAS and CMS because of the upgrade. This is a global picture of the accumulation of luminosity over the whole of run 1 and run 2. You can see the big performance improvements year to year. And this was the global luminosity total, integrated luminosity total, hoped for before LHC started up. If you add up all these runs, you see that all the experiments except LHCb got substantially beyond that in the end. So I realize time is going. I would like to tell you a little bit about what limits luminosity. I've stolen this slide from Peter Steinberg. As you know, I think, one of the subjects of study in the heavy ion program are the ultra-peripheral collisions. Due to the very strong electromagnetic fields, basically the strongest magnetic fields known in the universe occur around the lead nuclei in the LHC. Because of the large charge and the ultra-relativistic speeds, this Lorentz contraction is quite dramatic, much more so than shown in these images. And it's effectively a source of nearly real high-energy photons. You will probably be familiar with the equivalent photon approximation of Fermi, Landau, Weizsäcker, and Williams. The photon spectrum extends up to 80 GeV in lead-lead collisions, or 3 GeV in gold-gold at RIC. And the photons strengths, the coherent strengths scale as Z squared, which means they're much stronger for nuclei than for protons. So ALICE will study, for example, Jape psi production, but for the accelerator, we also have a number of processes that we are interested in. The most important one is bound-free pair production, where in these strong magnetic fields, you create, of course, abundant electron-positron pairs. In a small fraction of those events, the positron is born in a bound state of one of the nuclei. So rather than 208 lead 82 plus, it becomes a one electron ion with 81 plus. Other processes that are important are electromagnetic dissociation. These are photonuclear processes where one neutron is emitted from the nucleus, and therefore it changes its mass but not its charge, or also even two neutrons. What's interesting is that these processes have enormous cross-section, such as 281 barns at the LHC, or 96 or 29. So these are actually much larger than the inelastic hadronic cross-section, the 8 barns that accounts for most of the events that Alice or the other experiments look at. What this means is that we have secondary beams of modified ions emerging from the IP with a rigidity change delta in the case of BFPP, it's about 1%, which means that these ions are bent differently in the bending magnets and are actually lost and can potentially quench the bending magnets. So, and these beams actually contain significant power. To understand why these cross sections are so large, this is just a heuristic argument. If you look at the radio wave function of the 1s 1/2 state of a hydrogen-like atom in its rest frame, you know this from quantum mechanics, the wave function at the origin goes as z to the 3/2. Therefore, you can expect extra factors of z going up to z to the 7th in equal charge state collisions. And there is a logarithmic dependence on the center of mass energy, but you see that because of this very strong dependence on Z, for example, in copper-copper at RIC, the cross-section was only 0.2 barns, but it goes up to 281 barns for lead-lead. There are more detailed calculations, of course, which people have done. This is a paper we often refer to, which gave the values for the LHC. Concern about this effect was first raised by Spencer Klein back in 2001. Before even I was working on heavy ions in the LHC, he made some estimates which suggested that these losses could heat the magnet coils and exceed the available cooling, and therefore quench the superconducting magnets, bringing the operation to a halt, so limiting luminosity. This didn't have a proper model of the beam optics, but later we did this, and here is a beam envelope calculation of this bound-free pair production beam, these modified ions, deviating from the circulating beam of unmodified lead and being bent into the wall of the beam pipe here, a few hundred meters from the interaction point, and hitting the coils of a dipole magnet, essentially showering into them. This effect was first observed at RIC. We went to RIC and set up an experiment when they had copper beams, which reproduced a configuration similar to this with gold-gold. This beam doesn't actually hit the chamber, but propagates off around the ring, so it wasn't observed. Although the effects were very small, we were able to detect them with pin diodes, and here you see the losses correlated to luminosity. This was the first observation of this effect. In the LHC, you have to do a Fluke shower simulation typically to see what happens. Okay, I'm watching my time. I guess I will overrun a little bit, I think, but Siddharth told me this is probably okay this morning. Here is a heat map of the energy deposition in the coils unwrapped or azimuthally around the ring. And you get energy depositions of several milliwatts per cubic centimeter with even the old LHC design report luminosity. And for a long time, we were afraid that we would not even be able to reach the design luminosity in the LHC because of this. These are some of the engineering type calculations using special simulations, including the helium flow in the coils and this energy deposition and the effects of cooling. So there could be a couple of degrees temperature rise, which would be too much and stop the operation. Very soon in the LHC, in the first runs, we could see these effects here. This is an image showing the signals from all the beam loss monitors in the full LHC ring. And this is on a log scale because, well, that's the operators keep an eye on this all the time to see if there are large losses appearing. And here you can see around Alice here, around Atlas is split here, and around CMS here, you see substantial loss peaks due to this effect. These are the bound-free pair production peaks. Then I mentioned also there's electromagnetic dissociation effects. Those beams are, since they have a smaller rigidity shift, actually propagate around the ring and are finally intercepted by the momentum collimators. These are objects that are pushed close to the beam to take up particles that are deviating from the proper orbits before they can be lost anywhere else where they might do some damage or cause quenches. So in the momentum collimation sections here, you see these losses, although they're coming from the interaction points. And you also see losses from collimation inefficiency. Here in 0.7 of the LHC, you have the main betatron collimation system, which takes up particles that are deviating from the proper closed orbit for many possible reasons, for example, IBS. These collimators are designed to be the first things they encounter. This isn't an elaborate system, it has multiple stages. The trouble is it's designed for protons, and a proton, when it interacts with a collimator, typically made of carbon, it remains a proton, scatters off, and its secondary collimators can be inserted in positions where they take up these lost protons. It's a multi-stage system. This multi-stage concept doesn't work for nuclei because they fragment or undergo dissociation processes in the collimators. So you get many different isotopes coming out, and it's impossible to take care of all of them in a simple way with the original system. This is a complicated subject. I don't have time to discuss it, but for run 3 onwards, this will be one of the major limits, and we're now relying on a new crystal collimation system. I think there will also be update talks about that in Alice Week, not this one, maybe the next one. So how do we deal with BFPP? This shows the BFPP beams in more detail coming out of CMS. What we managed to do was to insert a bump in the orbit. I showed this yesterday around Alice. That pulls the losses away from the original loss point here shown in red, and means that the losses occur here where there is no dipole magnet. There's an empty cryostat here, and they can be lost safely in this way. So this actually allowed operation in 2015 and 2018 with higher luminosity at Atlas and CMS. We tested this strategy in 2015 in a special experiment where we set up the scheme at the beginning of the run and didn't touch it, but we didn't know whether it was really necessary because we didn't know the true level of losses that would quench the magnets. But what we did in an experiment was to set up a high luminosity fill, reduced those bumps and moved the losses back in to the connection cryostat, well, with low luminosity because the beams were somewhat separated. Then we increased the luminosity by manipulating the separation bump at the collision point to increase it. And all of a sudden, we saw a quench and the beams were dumped. This was the first luminosity-induced quench in the LHC at a value of 2.3 times design luminosity. We'd already been running at 4 or so times design luminosity in 2015. So in fact, we learned that we had been above the limit already. The strategy of the bumps worked and allowed high luminosity in CMS and ATLAS. In fact, it's quite interesting that we're using high field quantum electrodynamics here to quench superconductors. So there are interesting relations between what's going on at the collision point and what's going on in these superconducting magnets. These are the luminosity and beam loss monitors during this experiment. And it's been written up in detail in a physical review paper that we finally published about a year ago. Unfortunately, the strategy doesn't work for ALICE because the form of the orbits and the dispersion function in this section of the machine here, the so-called dispersion suppressor, is different from ATLAS and CMS because the polarities of the quadrupoles are reversed. The bump, the loss point would be here, and you can see that pulling this away, you cannot move it. It would just move a little bit along here and you can't get it into this empty cryostat. So the proposal made several years ago was to introduce new collimators shown here in black, which will intercept the losses. The loss would, if you pulled the loss away to the green position here, it would still be lost further downstream here, and you can't fix that. So these collimators have now been built and installed. This was a process that took some years, and they're ready for run 3. So this is the strategy that will allow ALICE to exploit the upgrade luminosity. ALICE can now take 6 times design luminosity instead of 1 times, and this will allow ALICE to accumulate much higher luminosity in run 3. Here is a schematic picture of this device inserted in this empty cryostat between 2 magnets. This is an actual photograph as it was being installed in the tunnel. So these devices are key for higher luminosity in ALICE in the future. We have unfinished business, and this is a little bit of a personal photograph because it happened on my birthday, which was the last few hours of run 2. We had a planned experiment to repeat this quenching experiment, a planned repeat of this quench experiment to resolve some ambiguities that we still had. Unfortunately, it failed because we had a problem with, it turned out to be a degradation of the stripper foil in those last few hours of the LHC operation in run 2. This is the team that were assembled to do this experiment. I should introduce you to Roderick Bruce, who is now the person mainly responsible for heavy ion beams in the LHC, so you'll no doubt hear talks from him. Other people who played a big role include Michaela Schaumann and Mark Jabramczyk for proton lead, and other colleagues here, Jörg Weniger, who of course you probably know as head of operations at the LHC, and others. So we hope that we can perhaps try this experiment again about 1 year from now. Another thing that happened, of course, with the xenon collisions in 2017, I'll like to mention this, it only accounted for 16 hours of beam time in total. No run was scheduled for heavy ions in 2017, but it happened that there were xenon beams in the injectors for fixed target operation. And we begged a little LHC time, we got 16 hours. During that time, we managed to set up a low luminosity xenon configuration. And the fact that this was a completely new type of beam in the LHC gave us many interesting results in beam physics, which were published mainly at this conference, particularly in the collimation system. There were, of course, in the subsequent Quark Matter conference, a huge number of different papers discussing results from xenon. And as you know, there were the data from those 8 hours of xenon collisions continue to figure in many ALICE papers in 2021 because they provide a valuable comparison with the other colliding species. So I don't have time to discuss proton-lead collisions. I'm going to leave the slides in here. You can perhaps look at them. I might perhaps talk about them on some other occasion. Proton-lead was not expected to work in the LHC, but it did work. I don't have time to explain this, so I will skip all these slides and just go to my summary. Well, there's the proton nucleus program status. We had one short run in 2012, and then the runs in 2013 and 16, and increased the luminosity dramatically during that time. Summary: all 21st century hadron collider experiments are now exploiting heavy ion collisions as well as PP. There is a lot of interesting new, often nuclear beam physics. In a few months total operation time, the LHC luminosity performance is now up to 6 times design, which is the level required for the future so-called high luminosity LHC. There are new paradigms for hadron collider commissioning and operation, where things change very rapidly as opposed to being kept constant and exploited for months on end. New modes of operation unforeseen for the LHC, the asymmetric proton-lead collisions, xenon, and very soon oxygen and proton-oxygen collisions, perhaps lighter species again in run 5 beyond 2030, which we hope you can look forward to for Alice 3. I would encourage you to try to listen to some of the other talks. Some of them occur in Alice meetings, but elsewhere also, on future performance, especially the big subject of collimation and the new crystal collimation scheme that will be a key to the future performance also. The new slip stacking injector scheme and the SPS, which, as I said, was first operated last week. These things are all coming soon. And even in the longer term, heavy ions at the future circular collider, the FCC-HH, which might be built at and operated at CERN in the, well, somewhere beyond 2040. Heavy ions have also been studied there. There are a lot of interesting new features and even higher luminosities potentially. You can see papers and presentations about that in various places. So I think I'll stop there for the moment and take questions. Thank you.
Okay, thanks a lot, John, for this nice discussion. So we are now open for the questions. So if you want to ask a question, please unmute and speak, or write in the chat box, or raise your hands, whatever you like. I do not see any. Maybe I have one small question, John. So are there constraints on the type of species which can be collided from the collider point of view? And if yes, then what are the determining factors?
Yes, you can't just pick any element out of the periodic table. Some are more difficult to deal with than others. If you've been following the discussions about future light ion collisions, you've noticed that we tend to favor the noble gases because those are quite easy to handle in the heavy ion source. The chemical aspects, let's say, of different elements are relevant, particularly in the source. Lead is actually not particularly easy. The lead pellets, we need to buy very expensive isotopically pure lead 208, not just normal lead, which is a mixture of isotopes, because that you would if you only use normal lead, you would already take a reduction factor equal to the percentage of lead 208 in normal lead, which I think is less than 50%. So it's worth buying the expensive lead, even though it's more expensive than gold. Other elements, the lead then requires to be vaporized in a little oven. This creates some problems. You get lead deposited around the source. The chamber may have to be replaced at certain times. With the noble gases, you just have to inject a gas and then start removing electrons in the cyclotron resonance. Other elements can cause other problems. Other metals have even higher vaporization temperatures, so they're more difficult. So on the whole, the noble gases and some other gases are the most convenient things to use in the source.
Okay, thank you. So in at LSC, one can also collide gold, and copper, from the technical.
In principle, yes. That's not under discussion. I think gold is not so different from lead.
Mm-hmm.
Copper is not so easy in the CERN source. The EBIS source at Brookhaven is, of course, more flexible. It's much easier for them to change species, but the ECR source that we have provides higher intensities ultimately, but it does take several weeks. That's another constraint, of course, that if you decide to change species, you need, well, at least it needs several weeks to commission a new species in the source and the injectors. So it's not easy to get several weeks of beam time in the complex. And even once you've done it and you know the right settings, it will take a couple of weeks to restore them. So you, for example, colliding oxygen with lead will never be possible in the LHC because you couldn't switch from oxygen to lead within one fill. It would take some weeks. So you can do protons since they come from another source altogether and another LINAC and so on, but not even deuterons. So there are some constraints there.
Okay.
The species being discussed for the future ALICE-3 might be oxygen, possibly oxygen, probably not, but perhaps argon, perhaps xenon.
Okay.
Discussions are ongoing, and of course it's difficult actually to estimate the intensities that you can get with other species until you've actually tried it. And trying it, as I said, takes some time. But there are plans to do some tests with various species in the injector complex over the coming years to better prepare the program for ALICE-3.
Okay, thank you. So now I have one question in the chat box. So Ronald, you want to ask, you can switch on your video and ask if possible, otherwise I can read it. Ronald? Okay, so let me read it. So the question is there any effect of beam energy on some of the effects you mentioned today? If so, how would it affect the beam luminosity?
Sorry, what was the constraints on beam energy? Sorry, could you?
Yeah, is there any effect of beam energy on some of the effects you mentioned today?
Yes, certainly, yes. Well, for example, the bound-free pair production process, the energy carried by these lost ions is, well, the power they deposit in the magnets depends on the luminosity, but of course also the energy carried by each ion. So there's a simple proportionality, and luminosity generally increases with energy. And moreover, the susceptibility of the magnets to quenching increases with their magnetic field, which is, of course, higher at the higher operating energy. So there could be an argument, for example, not to run at 6.8 TeV, but to run at 6.37 TeV if you're worried about magnets quenching from, not so much from BFPP, we believe we have solved this, but from the collimation losses, which are the remaining difficulty. So that's actually still under discussion, but going from 6.8 ZTV down to 6.37, which is the 2018 energy again, actually makes some difference. Many other things, for example, intra-beam scattering is worse at low energies than at high energies, with the other parameters are equal. Yes, all effects depend on energy in one way or the other, with different powers as well.
Okay, so Ronald, I hope you were satisfied with the answer. So now I have one more hand raised by Prof Das from Niger. Prof,
hello.
You can unmute and ask.
Yes, so I have come across this question many times. So just I want to ask, how do you decide these energies, like the collision energy for lead or PP, like 5.02 or 2.76 GeV?
Yes, okay. Well, I'll go back to that table I had at the beginning. There's a lot of history in that table. Well, 2.6 TeV per nucleon beam energy is, of course, the maximum nominal energy of the LHC. So that was in the original parameter lists. Yeah. Here's the table. So that was the original energy. It hasn't been operated at that energy yet. Back in 2010 and 2011, the beam energy was limited to 3.5 TeV for protons because of concerns about the magnets quenching if they were operated at high energy, even for protons, if they were operated even without beams. And that was increased to 4 in 2013. In 2015, it became possible to operate protons at 6.5 TeV, but we pointed out that it would be useful for heavy ion physics purposes to reduce the energy a little bit to 6.37 TeV proton equivalent, because this was a small loss in total energy, but it would give exactly the same center of mass energy as the 4Z TeV operation back in 2013. So the data on proton lead from that run could be compared with the data from lead in this run, which increases the precision of the comparisons, as you know, of the R factors and other quantities that are typically shown in Alice physics results plots. So that was a reason for choosing this special energy at that stage. And now the 7 TeV proton energy is still not quite accessible because there's not been enough time to train all the magnets. So run 3 will be done at 6.8 TeV proton energy, which will allow us to get to 5.36 TeV in lead collision energy. But there could be an argument for, as I just said, for reducing that back to the same energy as 2018, since the total energy is not so much different, but it would have some advantages for beam operation, might be a little bit safer. This is still being discussed a bit, but I think it's likely that we'll actually go to this energy in next year. And then perhaps in run 4, once the magnets have been trained, we will finally get to the nominal beam energy. Of course, then for comparison, there are special short runs with protons for comparison with lead at these low energies of 2.51 TeV to reproduce this same center mass energy per nucleon pair with protons as well. So you get it for PP, for P-lead and lead in different years and different runs. In future, there will, of course, have to be new PP reference runs that have to be scheduled in the program for comparison with the future lead ones. Also because the experiments like to have, although there is data at this energy already, they want data with the same detector. So therefore it means they have to be done essentially in the same year or not 2 different years. So the energies are chosen in heavy ion operation ultimately to provide comparisons with the experiments, although in some cases, for example, proton lead in 2016, one also went to the maximum possible energy where you see some effects better in operation. And of course, the luminosity is higher at high energy.
Okay, thanks.
Yes, so we can take 1 or 2 more questions. We have. So I already see a message from Priyansi. Priyansi, do you want to speak? You can switch on your video, audio and speak, or you want me to read?
Hello. Yeah.
Yeah, please go ahead.
I just had a small question. So how is the beam pipe material selected, and can it be the same for all the beam energies, or is there any effect that is taken into consideration?
The beam pipe in the machine as a whole, or in the detector?
In the machine as a whole.
And the machine as a whole. Okay, it certainly isn't changed for different beam energies. We couldn't rebuild all that.
Yeah.
That would be very difficult and expensive. I don't think there is any real reason for it. The beam pipe is, the beam pipe, I showed a picture of somewhere. No, it was in yesterday's lecture. There's a picture of it. You can see from the color that the inside of, well, there are actually two pipes. There's the beam pipe itself, the vacuum pipe. Inside it, there is a second kind of liner called the beam screen, which is another beam pipe inside the other one, which has actually got a lot of holes in it. The outer beam pipe does the cryogenic pumping because it's colder. The inner one is a bit warmer. It's at 20 degrees normally. Particularly in proton operation, the high beam currents induce currents also in the beam pipe. So these currents flow and create fields that can act back on the beam. The many holes are positioned at random to avoid coherence of these electromagnetic fields. The material of the pipe is aluminium, but there is a copper coating on the inner beam screen because it has a low resistance to these currents, of course, and therefore less dissipation of heat. There's a lot of technology in the beam screen, though. One should also have a lecture on beam vacuum and the properties of materials to understand everything.
Okay. Thank you. Thank you so much.
Okay, do we have any more questions? I don't see any. Okay, so from the organizing committee, on behalf of the organizing committee and all the students and everyone, thanks a lot, John, for your time.
Well, it was a pleasure. I'm very happy to have had the chance to speak to everyone here. It's a pity I couldn't come to India, but maybe sometime.
Yeah, okay. Okay, thank you. Thank you so much.
Thank you.
Okay, so then we move to